In this video, we're going to keep thinking about probabilities, and in particular, we're going to look at applications of the sum and the product rule that I introduced in the last video. I'm going to do a bunch of manipulations here that are going to seem unmotivated to derive a new result from the old result. Let's suppose that we want to reason about two propositions, A and B. All right, so we're going to find the plausibility of A or B, conditioned on some background information, and I'm going to insist on putting the bar with the I stating our background information that allows us to assign these probabilities. And so we're going to insist on this like they do in the textbook and in Jane's book, because all these probabilities reflect our state of knowledge. They're not something that we go out and measure in the real world. Depending on the information we have, the same propositions may have different probabilities, and so we need to condition it on the background information. So this, and we're going to now manipulate this first using the sum rule. So this will be the same as 1 minus the probability of not A or B. And now we're going to use the logical rule of duality to break this up. Not A or B is the same thing as not A and not B, right? If either A or B is true, then not A or B is going to be false. And now we're going to manipulate the second term using the product rule. So the joint probability for A and B being true is the same as the probability of not A being true multiplied by the probability of not B being true conditioned on not A. And now we're going to rewrite the second term using the sum rule again. We're going to do some algebra, simply multiply through this term, distribute it. And now we're going to combine this one, these first two terms, using the sum rule, and the second two term we're going to combine them using the product rule. And now we're going to break up the second one using the product rule, but now we'll break it up the other way. So notice here we have not A conditioned on I times the probability of B conditioned on not A. We'll rewrite it so we have B, probability of B conditioned on I, multiplied by the probability of not A conditioned on B and I. And now we're going to use, again, the sum rule on the second term. And again, we're going to distribute this one inside. And now we're going to combine the last term using the product rule. And this is the result that I wanted to get. So let me rewrite all in one line. And what does it say? It says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both A and B. So this is a result that maybe you're already familiar with from set theory, right? If I was to draw the sets, if I have and so it says that, so you can think of it like sets or like the areas. So the area of the combination of A and B is the area of A plus the area of B, but now we've double counted the middle, so we have to subtract it out. And so we've gone through this very complicated set of derivations that seem unmotivated to get at this statement that maybe we could have gotten much more quickly using set theory or Venn diagrams, which you may remember from elementary school, I think is when I learned about it. I don't know if that's still when they teach it, but I remember learning things about sets in like second and third grade. In any event, the reason why we go through this long derivation is because although they're equivalent, it's not always, or it's not obvious that when we're dealing about propositions, about the truths of various statements, that they can be mapped onto these areas, right? So that's something that's not so obvious. If I'm talking about probably there was life on Mars, or probably there was life on one of the moons of Saturn, for example. So those two statements are, it's not clear that we can break them up into little patches of area or points in this set. But nevertheless, they're equivalent. So I encourage you to use these Venn diagrams because they're much more efficient when thinking about probabilities. But it's important to know that our theory is not limited to things that are obviously mapped onto sets. And so the mathematical theory of probability that is the most accepted one, that's very rigorous, is based on Kolmogorov, and he couches everything in terms of a set of axioms applying to sets and functions operating on these sets. And it turns out that the rules of probabilities that we've gotten from Jaynes are equivalent to those of Kolmogorov. The only difference is how we think about them. So it seems that through the process in Jaynes' book, easier to think about them in terms of the validity of various propositions. But the rules and how we manipulating are the same as those you would find in a math textbook. For example, in Apostol's book, there's a very good chapter on probability theory based on the set theory, and it's pretty concise and easy to read. Okay, so that was a long derivation for this one. Now we're going to derive two new results from the rules of probability that are going to be easier to get at. So the first one is Bayes' rule. All right, so now we're going to derive Bayes' rule or Bayes' theorem. And so for this, we start off with the probability, two propositions A and B, conditioned on some background information, and we expand it out using the product rule. And now we're going to take this one and we're going to manipulate it in a different way. So we have the probability of A and B is the same thing as the probability of B and A by the associativity rule from logic, right? It doesn't matter the order in which we put the statements. And now we're going to expand this using the product rule. Now we've expanded A and B into two different ways, this way and this way. They're both equal to the probability of A and B, so therefore they're equal to each other. So what this gives us is this one equal to that one, and we're going to do more than that. We're going to divide through by the probability of A given I. So we have the probability of A and I after dividing through the probability of A given I, and is equal to this side divided by that probability. Now this result is Bayes' rule, or Bayes' theorem. And this is a very important result. It's very simple, but very important. It's because it allows us to update the probability of various propositions. So for example, if we have some knowledge of B, and we have some plausibility or probability assigned to B, and then we get new information, A, we learn about the probability of A, whether it's true or not. We can multiply these two together and then normalize, and then we can update the probability of B. So now we have the probability of B conditioned on A. So it allows us to go from this prior probability to this posterior probability where B now is conditioned on both this new information A and the background information, whereas before it was conditioned only on this background information I. So that's one way in which we can use Bayes' theorem. Another way why it's very useful is that maybe we can go back and we have the joint probability. If we can just assign the joint probability directly, then that would be great. We can then manipulate whichever way we want. But normally it's very hard to assign this joint probability. Our mind has a hard time modeling and thinking about this one. It's usually much easier, for example, to assign this probability here. This one, it's easy to find a model to it and to assign a probability to this one, and then use Bayes' rule to get an updated probability. So one pattern in which we use this is in the following way. So suppose that we interpret B as being some hypothesis or some theory, hypothesis, and A were some data that we've collected that is relevant to this hypothesis. We think that there's some global warming, the ocean's in warming, and so we go out and we collect some data, we take some cruises in the ocean, and we drop some CTDs, and we measure the sea surface temperature from satellites, and we combine this data. And now we're going to try to update the hypothesis that the ocean is warming due to global warming. So we may already have some prior knowledge on what this is based on theory, so that would be the probability of B conditioned on the background information. So it doesn't depend on the data. So this is our prior, so this is known as the prior, or prior probability. And this one over here, this is the probability of the data conditioned on B, which is the hypothesis, and the background information. That's what we're calling probability of A given B and I. this one, we call this a likelihood. And the reason is that here we're assigning a probability to the observations based on our hypothesis. So for example, the hypothesis might be some numerical model of the ocean and the theory of the Earth's radiation that allows us to predict how much warming we can expect. And so we can assign a probability to the data. We've measured the ocean temperatures conditioned on our hypothesis or our model being correct. And now what we're going to do is we're going to flip it around and using Bayes' theorem to get on this side the probability of this hypothesis that the ocean is warming. So this becomes probability of the hypothesis. Addition now on B, which is the data, and the background information, which is going to be proportional to this prior probability times the likelihood. And this is, we don't need to put in the probability of A because it doesn't depend on the hypothesis. Very often for parameter estimation, we can ignore this one. There'll be cases where we need to know about it, but for now, many cases we don't need to know. So see what we've done here. We had some prior probability on some hypothesis, and we used the Bayes rule to relate it to the probability of the hypothesis conditioned on the data. So we had the probability of the data conditioned on the hypothesis, and I claim that this is usually much easier to assign a probability model for the data conditioned on the hypothesis than it is to go the other way around and assign a probability directly to the hypothesis based on the data, or assigning a probability to the joint event, the hypothesis and the data. These are hard for us to think about, but these two are easier. And then we use Bayes' rule and we update to invert. We basically invert the probability of the data conditioned onto the hypothesis into the probability of the hypothesis conditioned on the data. And this is the pattern, the main pattern of reasoning that we're going to use to analyze data, and we're going to give examples of this very soon. All right, so the other rule other than Bayes' theorem that we're going to use a lot is called marginalization. Pattern this time is, suppose that we have the joint probability for both A and B, and we want to get the probability for B alone. So we're going to have very many opportunities where we've derived a joint probability for two quantities, but only one of them is of interest. Suppose we only care about B, but what we have is the joint probability for both A and B, and we want to get the probability for B alone. So we can do this in the following way. So the probability of B, conditioned on the background information, is the same thing as right, so this here, by the sum rule, this has to be equal to 1, right? It's the probability of A plus the probability of not A. They're conditioned on the same quantities, and so this is just equal to 1. So we didn't change anything, we just multiplied by 1. And then we can distribute B inside. And then we can join both of them using the product rule. So this one becomes the probability of A and B, oops, conditioned on I. This one and this one becomes the probability of not A and B, conditioned on I. And so this is the same thing as the sum. So it's the sum of both cases, A or not A. And we start off with the joint probability, and by summing all the exhaustive cases for what the probability of A is, we ended up with the probability for B alone. And this can be generalized where A can be broken up into a whole bunch of different propositions. So we will get in general the probability of B alone is equal to the sum of the probability of A sub I and B. And this again, we've taken the joint probability for A and B and we've summed over all the possible cases for A, and we've ended up with the probability for B alone. And if A was a continuous variable, then we can write it this way. Probability of B conditioned on I is the integral. So here I have to make sure that I clarify a point that usually confuses the students, is that over here, these quantities in this discrete cases are all probabilities. So they're dimensionless, they're just numbers between 0 and 1. In this case, although we called it probability again because it's convenient to do so, but we have to multiply by dA in order to get a probability. So in this case, this is a probability density. So it's the amount of probability per unit interval of A, of the quantity A. So if this was measuring the length of something, A would have units of, let's say, meters, and this quantity here would be the probability, the joint probability for A and B per unit length of A. And then when we sum this, we end up on this side just the probability for B. Now, if B was also a continuous variable and this was also a probability density, then this one would have, suppose, B as units of mass, for example. So this would be the amount of probability per unit mass, and this one will be the amount of probability per unit length and per unit mass. So it's a density. All right, so this rule is called the marginalization rule, and it is also quite useful when we're going to do data analysis. We'll have the opportunity to use this quite often.